Okay, Marnie, if you can hold this bucket just over there.
Sure. This is very exciting. You can see why people go crazy for this. This is Crowd Science from the BBC World Service. I'm Marnie Chesterton and I'm up to my thighs in a Scottish river. I'm wearing waders. It's a beautiful, beautiful Scottish sunny day. The views around me are amazing, but I'm not here for the views. I'm here for something beneath my feet. Hopefully, I'm going to find gold.
Okay, let's go.
What's this tool called?
This is a suction pump, and what it does, it will suck up all the material, and you can see it's coming up grey. That's the bedrock. That is actually...
That's the good stuff.
Yeah, it's basically decomposed galena, which is lead. This is a lead area from the lead mines, and that's where the gold and lead tend to go quite well together. So next, fingers crossed, it will have something. It's very unusual to get that colour, but it's possibly a good sign.
I think you should maybe manage my expectations, because I've got my licence, I've got kitted up. How likely am I to make my fortune today?
You're very unlikely to pay off your mortgage today, but I think we're going to find some gold today. I've just got a good feeling that the sky's clearing, the sun's come out, that hopefully the gold's going to glint at us.
Well, before we get into the hard work, I should probably mention this isn't a get-rich-quick scheme by the Crowd Science team. We've actually come here in search of audio gold as well, and the answer to a question from one of our listeners.
Hello Crowd Science, this is Martijn from the Netherlands, and I have a question about natural resources like valuable minerals and metals. These are distributed unequally across the globe, and I'd like to know why. Why are high concentrations of things like gold and silver, cobalt, lithium, potash and many others found in certain places but not in others?
Martijn, welcome to Crowd Science.
Thank you.
From your emails, I've seen that you're quite well travelled, aren't you?
I've been to a few places, but of course there's many more places I haven't been to.
And you just keep noticing wherever you go the legacy of human efforts to mine minerals, right?
Yes, well, I was once in Death Valley in the United States, and I saw these tunnels being dug, or that had been dug in the distant past, and these turned out to be thin veins of gold. And so I wondered, why is there gold exactly there and nowhere else?
I take it there's never been a gold rush in the Netherlands.
Well, not as far as I know. I don't think so, no.
So why do you think it's important for us?
Well, we're kind of dependent of quite some different elements. Most of our technology, we're using it right at this moment, requires various elements, and they need exactly those elements and not others to make radios work, to make phones work, and to make windmills work properly and solar panels. So we desperately need them.
Everything you can see, and quite a lot that you can't on this lovely planet we live on, comes from 92 elements. Where they came from is another story, and one that Crowd Science has looked at before. Check out How Old Are the Elements in our archive. In today's show, though, we want to know why, after billions of years swirling around, the elements aren't yet thoroughly mixed up. Why, for example, do we find no gold in my backyard, or Martijn's, and whole shiny chunks of it elsewhere? Hopefully in this Scottish river.
So I think we've sucked up enough material, and we're just going to get rid of the bigger stuff. We always just check the classifier, the sieve, to make sure there isn't a big nugget lying in there we're going to throw away. So you can see there's nothing there. So we'll now get a gold pan, and we're going to pan the material that we've just brought up from the riverbed.
Let me introduce Leon Kirk. He's an expert gold prospector, and he's in the water alongside me, giving a lesson in how to pan for gold. Right, what now? I've got a gold pan, you've got a bucket full of grey water and sludge.
So we'll just make sure we get every little bit out the bucket, because obviously the gold will try and hide in the bottom of the bucket. So that's the bucket, lovely and empty. So at the front of the pan we've got what you call riffles, and these are the ridges. So what you always have to do is have them at the front end of the pan, and when we shake the material, The heavier material will go to the bottom and the lighter material will come to the top.
So I'm knee-deep in this Scottish river looking for gold. But why is it here? Where did it come from? I think it's time to call Holly Elliott. She's a lecturer in ore deposits at the University of Derby in England, so she ought to know.
Well, it's very much connected to all of the geological processes that have occurred in that certain spot over the world's history, so over geological time. And when I'm talking about geological time, I'm not talking about a watch, I'm talking millions to billions of years ago, so the entire duration of the planet's formation.
So let's talk about what happened during those billions of years. The place to focus our attention is the Earth's mantle, a layer of this planet about 1,000 kilometres thick, which sits just below the thin crust that we live on and call the ground. Down in the mantle, there are all sorts of elements, metals and minerals, but they aren't spread out evenly. The reason? It's because of the way the mantle interacts with massive sections of the surface sitting above it, known as tectonic plates. I'll let Holly explain.
They are essentially bits of rock that are moving around on top of the mantle underneath our feet, and we have oceanic plates which make up our ocean basins, and then we have continental plates which are what we actually live on. And all of these have collided, they have been pushed one underneath the other. We also have material coming up from depth. So if you think about a lava lamp with globules coming up from below and bringing stuff higher up into the surface, and also stuff being pushed in from subducting plates from on top, we eventually end up with areas of the mantle which have more elements of one thing and others which have more of something else.
So, deposits of particular kinds of metals and minerals, they get moved around by these plates?
So it's not as simple as that, unfortunately. What we have is geological processes that are linked to the tectonic environment, and these processes are called enrichment processes. So they take metals from one place and they deposit them somewhere else. So they actually increase the average concentration in the Earth's crust. So if we take copper, for an example, the amount of average copper in the Earth's crust is 0.0068%, an absolute tiny amount. But in actually, to make it economic to extract, a copper mine must contain around 2% copper. So that means that we need to enrich it or concentrate it by a factor of 294 times, which is an incredible amount. And that requires a series of different geological processes, or what we call enrichment processes, to actually get it to that point.
Imagine a big bowl of grains of rice. Now, chuck in 10 grains of wheat and stir. If you then found all your grains of wheat clumped close together, you'd think, hang on, how did that happen? That, on a much larger scale, is Martine's question. And the answer involves certain processes. What processes? Well, according to everyone we ask, it's complicated.
So, it is complicated, I will say it, because there are many different types of deposits and they form in many different kinds of ways.
That's Professor Jamie Wilkinson. He works as a researcher at the Natural History Museum in London.
So we can simplify it down to three main groups of deposits. There are surficial deposits that form through basically weathering or sediment transport processes. So bauxite, the aluminium ore, is a good example of that. A lot of the elements get preferentially dissolved and removed in groundwater during the weathering process, but the aluminium is immobile. It doesn't like to move in low temperature groundwater, so it gets left behind and gradually concentrated during weathering. And in some places it gets concentrated sufficiently so that it can be mined as an aluminium ore material.
Ore, a word you'll be hearing a lot. Not as in awesome, although the mountain moving processes that make them are pretty impressive. Or as in chunk of this planet that has enough metal or mineral in it for humans to bother taking it out.
Second major group of ore forming processes are magmatic ones that are purely involving molten rock, so magma. And they form from a process we call sulfide unmixing. So the normal magma is made of silicate materials, lots of other elements in there as well as silicon. But what can happen is that a separate melt of sulfide can form. Under certain conditions, the sulfide separates out. So you end up with two melts, silicate melt and then this dense sulfide melt. And certain elements that really like to bond with sulfur jump into the sulfide melt preferentially and get concentrated in that process.
What's going on there? Why are certain minerals, certain elements found together?
So the chemistry of how things behave in mineral deposits is related to the properties of the elements. So if you think about a periodic table of elements, then elements in certain parts of that periodic table have very similar chemical characteristics. So they tend to go together in a geochemical process. So again, nickel and copper with similar properties move into the sulfide melt and get concentrated. But when it binds with these metals and crystallizes, it will form an ore that will have a metallic luster to it. So they're like steely or golden, coppery color metallic minerals that would form in those types of ores.
Forming ores over thousands or millions of years, it's like a recipe. You need the right ingredients and the right conditions. And some of those conditions happen at the Earth's surface. Others, magmatic processes, they take place below the surface. But the biggest and most diverse group of ore deposits are formed by a process known as hydrothermal.
So they're formed from the action of movement of water in the earth through cracks and fissures, usually hot water, maybe up to 600 degrees Celsius, so magmatic temperatures, all the way down to very low temperatures. But metals can dissolve in those waters under certain conditions and then move through these cracks and then get deposited somewhere else. And if the process of deposition is efficient, a lot of the mineral is precipitated in one place, then you could potentially form a hydrothermal ore deposit.
Jamie talked there about mineral precipitation. Precipitation to me means rain, but in the world of chemistry and geology it's a bit different. Here's Holly again.
So precipitate is very similar to crystallizing out of a fluid. So if anybody has ever heated up salt in hot water and then let it cool down, you'll notice that you actually get crystallization of that salt back out of the water, and that's what we call precipitation. So any water that's containing a lot of elements like metals, for example, as it cools down, or if it neutralizes, it could be acidic and it neutralizes, it will drop whatever it is it's holding, and that dropping process is what we call precipitation.
Earlier, Holly mentioned that to get a mineral in a high enough concentration that it's worth extracting, it had to go through a whole series of different processes. So, what's the story of how gold ended up in a Scottish hillside?
Scotland never used to be attached to the top of England. There used to actually be an ocean in between England and Scotland. And the oceanic plate that was between us was subducted underneath Scotland, which caused Scotland to collide with the top of England. And that created huge amounts of pressures, which squeezed the continental crust that we're sitting on. That generated water, which allowed it to mobilise the gold that was within the crust. So that hydrothermal fluid we were just talking about stripped out the gold that was within the crust and then precipitated it, so concentrated it higher up within those golden quartz veins.
So we're taking it left to right, so what it's doing is dropping the heavy material to the bottom of the pan and the lighter materials to the top of the pan, and then we lift the pan out of the water at the right angle and it will just take off the top all those little stones on the top, the lighter material.
So if you power washed the side of this mountain, you'd see rock with quartz veins running through it, caused by those hydrothermal processes, and some of those veins would contain gold. The mountain then gets weathered and eroded, releasing pieces of gold that have, hopefully, ended up in this river.
You can see it's now turned black and red with hematite, which is a good sign.
That's the iron stuff that you find near the gold.
That is it, that's the hematite. So we're in the last part of the pan, and what I'm going to do is do a different process now, is tilt back the pan, and what we do is just slowly eat away at the material, just to expose all the last little bit of material. So we're just gently doing it, and you can see that's lead and hematite there, all the heavy minerals of the river. That's very heavy, that. There's lead shot, someone's been shooting in the area many moons ago. And guess what?
No gold. Oh, no. What's that?
What's that? What's that?
First pan and we found gold.
First pan and we found gold. There you go. That's absolutely amazing. So there's 1, 2, 3, 4 pieces of gold there.
So these things are kind of like specks of pepper.
You've got it in the end of your finger, and that's
And
it.
I've just dabbed my finger in and I've got these 2 specks. I mean, they're very small, but they are very noticeably yellow gold. Wow, you found a big piece.
I think that's a big piece of gold.
I mean, I say big piece. Again, I'm dabbing it onto the end of my finger.
That's quite a nice little show of gold there. So, well done.
I can see how this gets addictive.
So, yeah, it is a nice little show of gold. Time to save it, yeah?
How much is that worth? Those tiny specks?
A few pounds, actually, believe it
Really?
or not, because it's so rare.
That's
a
extraordinary.
really lovely start for the day. It makes the sun come out, doesn't it?
It does.
We found gold, but it was only there through a set of specific circumstances and coincidences that happened throughout geological time.
There has to be gold there to start with in order for the hydrothermal fluids to have stripped it out. There needs to be the right sort of pressures to form those hydrothermal fluids and allow the mobilization of the water. And also, it's the way that the gold is precipitated. It has to be a sudden precipitation, because if you had a very slow cooling down of fluid, actually your gold would be strewn over quite a large area as it cooled quite slowly. You need a sudden rapid drop in temperature, so it all drops it in one specific spot. That means you've got a large concentration and therefore you've got a nice rich gold deposit. Or you need that acidic fluid to react to something, to neutralize, and if it's neutralized, it's not as good at carrying the gold, so again it drops all of the gold in a specific place. So you need a certain set of factors to all combine together in order to form that gold deposit. And again, that's why as an economic geologist, we always come back to the Goldilocks effect. It has to be just the right set of conditions.
This is Crowd Science from the BBC World Service, where we're answering a question from one of our listeners, Martijn, about why precious minerals and metals are found in some spots and not others all around the world.
Now, earlier Martijn mentioned how certain specific elements are important to our modern way of life, as well as to the transition to a carbon-free future. And one of the most crucial elements for that is lithium. Lithium is used in rechargeable batteries for mobile phones, laptops and electric vehicles. And last year, around a quarter of the world's lithium was produced in Chile. But why? Why Chile? Well, Jane Chambers is here with us now. And Jane, you live in Chile, so tell us where you've been for Crowd Science.
Well, I went to the north of Chile to SQM's lithium plant in the Salar de Atacama, and this is like a 2-hour flight up from Santiago. It's surrounded by mountain ranges, and it's the largest salt flat in Chile, so these vast expanses. And I was there to try and find out why it's such a great spot for lithium. It really is like being in another world here. You've just got these vast open landscapes with the blue sky above and the sun burning down. Even though it's kind of autumn, winter here in Chile, it's about 22 degrees, really hot. We've all had to put on sun cream. In fact, I'm just rolling down my sleeves because I'll get told off. And there are mountains all around us, just mountain ranges, these beautiful different types of brown.
I'm Corrado Torre, I'm the manager for hydrogeology here at the Salar.
And where are you taking me in one of these lovely fancy red trucks? Where are we going?
We are going now to this little mountain, and it's the tallest place here at the Salar, so we can have a very good view of this very flat place. Veramente mi adelanto un poco para conversar con Jane.
It really is vast, isn't it? We've got 360-degree views. We've got mountains in the distance as far as the eye can see. And then a few I can see in the distance like a field. It looks like it's snow, but that's salt. And brown, just colours brown everywhere. It's so arid here, this dry desert. But how did the lithium get here in the first place? That's got something to do with the volcanoes and the ash, hasn't it? And the plates.
Exactly. I mean, first of all, volcanic ashes, volcanic rock is rich in lithium. And you have plenty of these here, outside and in the underground.
So those mountains in front of us, those are loads of volcanoes and volcanic rock.
Exactly, and that's rich in lithium. Then you have water, able to lixiviate this. First of all, water leaches the rock and extract something that is solid at that point and transform it in something that is liquid. That's the first part. Then you have hydrothermal fluids, something that is coming from the underground, very hot and rich in lithium in itself.
And lithium's a very light metal, isn't it? And it always wants to escape. It wants to get to the ocean and run away. So what is it about here that means it can't escape?
First of all, it's a closed basin.
And what's a closed basin?
Well, there is no other place to go. So all the things that enter this big, say, called stadium, go to the center, to the field. There is no escape from here because there is not so much rain, sun, wind, very dry air, so it's perfect for evaporation. And lithium cannot evaporate. There is no way out for lithium. And so you have a brine that was, at the very beginning, say water with a bit of salt in there. But after millions of years, it comes more and more concentrated.
So I've heard that you can get lithium pretty much everywhere, even in the oceans. It's just this business of how you extract it. And because you've got such good climatic conditions here and geographical conditions, you've got some of the best concentrates of lithium here in the world.
Exactly.
Jane, I have to say, I don't know if you got an aerial view of the place on the way in, but I've been looking at aerial views on Google Maps, and it's an extraordinary place. All of these different pools, they're square and they're lined up, and they're all these different hues of blues and greens and yellows, and it looks like a kid's paint box.
Yeah, it really is beautiful. You get an aerial view as you fly in of just how arid the desert is. It's a bit like landing on Mars. But you're right, they really are the most beautiful colours.
So you've established how the lithium ends up there in the first place, but at that point, it's still not concentrated enough to extract raw, is it?
No, the whole process can take between 12 to 14 months, and it involves pumping up the brine and passing it between these man-made pools, and that's where the sun evaporates it because it's so hot there, and it slowly gets more and more concentrated until it's ready to be taken to another plant in Antofagasta for the final processing. That is the sound of brine being pumped out of a black pipe into one of the ponds from another pond, because this is all about the chemical process and getting the balance right. So they'll be constantly monitoring things and seeing how the evaporation process is going and what the lithium concentrates are. And there are 4 different pools in front of me, all of different colours depending on the chemical makeup inside. One of them looks like there's been a lot of evaporation. The brine looks much thicker. It's got this kind of salty crust on top of it.
Wow, it sounds like you're by a waterfall, so it clearly takes a lot of brine to get the lithium out.
It absolutely does, yes. They're busy kind of pumping it from pool to pool in various degrees of intensity.
And then at the end of all of this, did they show you some of the lithium that they take out of the plants? Did you get to play with it?
Yes, it was really great. So at the end of my tour of these various ponds, I was taken to a storage type container where visitors are allowed to finally get their hands on some of the lithium. I've got a blue glove on, and in front of me there is a pond of very concentrated lithium, which looks like kind of murky pea green by this stage. And I've just been asked to put my glove into the water, where it's all kind of mudgy, like hard salt, and then they're just pouring water on. Ooh, weird. It heats up. In my hand, it's really weird. The reaction with the water heats up. It's fun.
Now, whether it's lithium mining in Chile, cobalt mining in the Democratic Republic of the Congo, or gold mining in Scotland, mining companies need to know where to dig. And as more and more of the Earth's known resources are extracted, the harder it becomes to find new ones. So, when I was at the Natural History Museum in London, I was taken behind the scenes to have a look at one method they're using to find some of our unequally distributed minerals.
Hi, I'm Yannick Bure. I run a laser ablation lab, and we are now in the Imaging and Analysis Centre in the Natural History Museum.
Laser ablation.
Yes.
What is that?
So, essentially, it's a laser. We fire it at a polished bit of rock or mineral, and that vaporizes that bit of sample, and we transport that vapor or aerosol into a mass spectrometer where it gets ionized, and we can analyze the different elements and isotopes.
Okay, so kind of the laser does the drilling for you.
Yes.
And then we've got something on the go.
We have.
What's in there right now?
So right now we have some zircons. So these are probably the best mineral to look at timescales back in deep time. So we're analyzing it for uranium-lead composition, and based on the amount of lead to uranium, we can tell what age a sample is to within percent levels.
I mean, what ages are we talking about?
So the minerals I'm analyzing now are around 1,000 million years old.
Okay, old stuff. Because you've got this camera set up, I can see this little blue light go off when it drills a tiny little hole into the surface of the rock. And there are dozens of these holes.
Yes.
How big are those holes?
So these holes are 25 micrometers, which is about half the width of a human hair.
So the laser is melting a tiny bit of the rock.
Yes.
And then what happens to the melty rock?
That recrystallizes and stays behind, but most of the particles are ejected from that, and they are transported through this tubing into the mass spectrometer, where it gets ionized in a plasma that is, I think it's 10,000 degrees Celsius, and it's hotter than the surface of the sun.
Sorry, inside that machine is hotter than the surface of the sun.
That white light there, yes.
Oh, okay. Should I be staring at it?
Yeah, it's fine.
Okay.
There's a shield.
Good to know. Thank you. So, the little particles get into they're heated super, super, super hot.
Yes, get charged.
And you can read the results on this computer screen over here.
Yes.
What's it tell you?
It tells us the amount of specific isotopes, so the amount of that element in that mineral.
Okay, so if, say, I was searching for gold,
yes,
then I'd be looking for a particular spike on the graph that corresponds to
gold, yes.
To gold. Okay.
Blasting rocks with lasers and heating them to temperatures hotter than the sun is undoubtedly a lot of fun, but how does it help us in the hunt for metal deposits? I asked Jamie Wilkinson.
So the minerals are small grains, and then we're analysing these really, really trace components, but that very subtle fingerprint in certain rocks can tell us that we may be in the vicinity of a deposit that may be buried beneath the surface, so there may be no surface expression of it that we can see, but there's a signal in the surrounding material around the outside of the deposit that we can pick up with this technique that can tell us that we may be on the edge or just above a major deposit of metals.
So hang on, so there's no tell on the surface, but you reckon a kilometre down there might be, I mean literally a gold mine, but there might be something that's really worth digging up. But what are the tells that you can find that mean that you don't dig for a kilometre and find nothing?
In the end, the only way you can know if there's something there is to drill a hole into it and get some samples back. But it's very expensive to do that. So part of what we're trying to do is to reduce the cost of that by making sure that drilling is in the right places. So how we do that is we use the fingerprint of certain minerals to help guide us in towards the center of these systems. And I'm talking particularly about hydrothermal systems, and we work a lot on major copper deposits. And how this works is we use the laser system, and we are analyzing minerals from rock samples across the surface in an area where we think there may be potential. And then what we're looking for is subtle signature of the halo of the deposit. So the ore in the middle, or buried at depth, is really quite a small volume. But when the deposit formed, the fluids that made it would spread out into the surrounding rocks and gradually move away and cool and react with those rocks. And they would leave this little trace fingerprint behind in some of the minerals that are forming. And this may be several kilometers away or above where the deposit itself sits, the economic resource. And in fact, there's a gradient in those compositions. So you might see an increasing concentration of a certain element or a decreasing concentration of a certain element that points you towards where the center of the system is. And obviously that's where you would want to make your drill hole.
I also heard that there's a lot of dissolved metals, so for example gold in seawater, which just, I can't help but think, if someone developed a bit of kit that could help you get out the really small amounts of gold that are in seawater, then is that an alternative? Is anyone looking at that?
Well, that's an interesting question. And in fact, every element of the periodic table will be dissolved in seawater. So you think, well, why can't that be a resource of everything we need? So the problem is the concentrations are so low that it would take a huge volume of seawater to extract anywhere near the same amount that we would get from even a single ore deposit. And B, the technology required and the cost involved of doing that extraction would be enormous. So it would be many, many, many times more expensive to do that than it would be to find a new deposit and develop a mine. I mean, some of the elements we're interested in may be at concentrations 1 billion times lower in seawater than they might be in a place of the Earth where they've been concentrated by the sorts of hydrothermal processes I've been talking about.
So, there's a little bit of an answer to Martijn's question. The ocean, which covers more than 70% of the planet, does contain all the elements you might ever want. But our perception of where minerals are found is often based on where they're extracted. In other words, where the concentration is high enough for it to be economically viable. And that's just as true under the ocean as it is on land. So far, we've been talking about how different minerals and metals end up in different places around the world. But wouldn't it be so much more convenient and leave fewer of those mining scars that Martijn mentioned if we could just find one spot with all of the good stuff together? Ideally in some sort of lump that you can just harvest like potatoes. Guess what? They do exist. Let me introduce you to polymetallic nodules, containing
metals like copper that we need for electrical technologies, we need rare earth elements for wind power, we need cobalt for batteries, and there is lithium in there, there is nickel. In principle, you find more or less the whole periodic table at variable concentrations, and that's why they are called polymetallic nodules.
That's Professor Andrea Kaczynski. She's a marine geochemist at the International Jakobs University in Bremen in Germany. And to find these nodules, she's taking us 4,000 metres down into the deep sea.
They grow very slowly, about a centimeter per million years, and so they are like potato size and potato shaped. So each manganese nodule is many millions of years old, but with this very slow growth it also accumulates trace metals in the ocean that have entered at very small concentrations, but due to the long time of enrichment these metals get very highly concentrated.
So on the ocean floor are these metal potato shaped objects. So what's going on? How do all of the metals just decide to clump together in this one object?
So usually nearly everything that ends up in the metals comes from the surface. Much of that is river-derived material or from atmospheric input from dust. So this is particles that are discharged into the ocean and that sink to the seafloor and they form the sediment. But much of that is also biological materials, where plankton starts as a first step of the food chain and then higher organisms, and when these organisms die, they sink down to the bottom. And when they sink to the bottom, they are continuously degraded, especially the organic carbon is released back into the ocean. But when these particles end up on the seafloor after a journey of about 4,000 meters, then there is still quite a bit of material in these particles, and this is organic matter. and this is also metals. And this little bit of organic matter that comes down to the seafloor is very precious food for microbes living in the deep sea because they don't have any other food source. They depend on what comes from above. And so they start recycling this organic matter, and this leads to a release of the metals, and then the metals start to move in the sediment and start to accumulate around a kind of nucleus. This nucleus can be a fish tooth or a larger pebble or an older ferromanganese nodule. And then layer by layer, these metals start accreting around this nucleus and grows.
That's fantastic. So they need, you said a fish tooth maybe?
Yes, for example, a shark tooth. That would be a typical finding if you open such a ferromanganese nodule.
So let me get this straight. There's organic material that just falls to the bottom of the ocean, and that is fed on by bacteria at the bottom of the ocean, and they produce metal ions as a byproduct of that, and those stick on something if there's something there to have metal stuck on them.
Yeah, that's in principle right, exactly. This degradation of organic matter by the microbes, that creates a special geochemical environment on the bottom that leads to the release and the movement of the metals.
So, these amazing nodules might contain every single known element, but just like deposits on land, they are also unevenly distributed. And again, that's because the circumstances have to be exactly right.
You need very special conditions with enough biological material and particulate matter raining down to the seafloor, but not too much. And that is why we do not find ferromanganese nodules ubiquitously distributed in the oceans, but preferentially in certain places where we find these prerequisites.
I also like the idea that you can kind of cut them in half and find out what's at the centre and go, oh, that one's a shark tooth.
Yeah, and it's interesting also because they look like tree rings, these growth rings of these ferromanganese nodules, because each of these growth layers, for example, is an ice age or an interglacial or something like that. So you can often already visually see the difference in composition by different colors or structures. And you also, of course, see it in the mineralogy and in the chemical composition of these individual layers. And so it's very exciting for us. Because they tell us a lot about the past millions of years of Earth history and how ocean circulation has changed, how the climate has changed, and things like that.
You can sense there's a but coming here. These nodules are the mineral equivalent of fossil fuel resources in that they took millions of years to form and we can only harvest them once. A highly polarised debate rages over whether to dredge them up from the sea floor. But there's no doubt that there remains a huge need for metals in the coming years.
With the transition to a carbon-neutral society, we need renewable energies. But what most people are not aware about is that renewable energies require a lot of non-renewable resources like metals. This means, because they are not yet in the cycle, we need to mine them. And the question is, where do we want to get them from?
So it's a one-time thing, because you were saying these things take millions of years to form.
They are non-renewable on human time scales, exactly.
So, Martijn from the Netherlands asked why valuable minerals and metals are unequally distributed around the planet, and we've discovered that the origin story of any mineral deposit depends on the particular circumstances. The conditions involving vast temperatures and pressures, maybe hot water trapped underground, maybe the presence of other helpful chemicals, all taking place in the swirling mantle and grinding tectonic plates of this planet over millions and billions of years. Often, the recipe to create a high enough to be useful concentration of any one ore takes several processes, round after round of heating, cooling, squashing, weathering, or slowly building up on the surface of a dead shark's tooth at the bottom of the ocean. Terms and conditions apply, and they have to be just right for a deposit to form. Usually, they aren't, and that's why there probably isn't gold in your backyard. As a commiseration, I hope we've provided a gold mine of interesting knowledge, and here's listener Martijn with the credits.
So that's all from this episode of Crowd Science from the BBC World Service. Today's question was from me, Martijn, in the Netherlands. It was presented by Marnie Chesterton and produced by Ben Motley. If you have a question and you'd like the CrowdScience team to mine the world for an answer, send it to crowdscience@bbc.co.uk. Thank you for listening.